Hello everyone, I am Irana Santi, the leader of Team VAYUVARGA. Our team problem statement ID is SIH1602, Team Space Technology, and Team ID 40477. Before going to our idea, we must have to know what is space debris. Space debris refers to the non-functional artificial objects in Earth orbit which may cause danger to the upcoming space mission. By 2019 estimation, the average space debris in LEOs are 6,000 tons. So now I have a small representation of the problem.
28 million objects larger than a millimeter are orbiting the Earth, transforming the space around it into a junkyard. These objects range from inactive satellites to flakes of paint. But even a millimeter of cosmic junk traveling at extremely high speeds can be catastrophic to many satellites that connect us around the world. Indeed, a fleck of paint was enough to damage a window on the International Space Station in 2016. So where does all this space junk come from? Why is space junk dangerous? And most importantly, are we doing anything about it? We have been sending satellites to space for over 60 years. So far, we have sent over 11,140 satellites in Earth's orbit. Out of these, 3,372 satellites are currently active. The rest are inactively floating in our orbit. The number of satellites has increased drastically over the past few years. In 2020 alone, 1,283 satellites were launched into lower Earth orbit. This is the highest number of satellite launches in a year to date. Now the low Earth orbit is about to become even more crowded. Over the next few decades, SpaceX is hoping to send a constellation of 42,000 satellites. Amazon's Project Kuiper, OneWeb Corporation, China's Hongyan, and Canada's Telesat are also planning on placing thousands of satellites of their own in the Earth's orbit. All that space traffic can lead to a disaster. The first documented collision involving space debris happened in 1996 when a French satellite was struck and damaged by debris from a French rocket that had exploded a decade before. In 2009, a U.S. commercial satellite, Iridium-33, collided with an inactive Russian communications satellite, Cosmos 2251, at a speed of 22,300 miles per hour. The collision created 2,300 pieces of space shrapnel, which now pose a threat to other spacecraft in low Earth orbit. This was the first known case of two satellites colliding catastrophically in space. Now, with tens of thousands of satellites traveling around 17,000 miles per hour, the chances of these satellites getting close to each other are a lot higher. Collisions between high-speed objects in orbit can create thousands of pieces of debris. This could result in a chain reaction where more and more objects collide and create new space junk in the process, to the point where Earth's orbit becomes unusable. The Kessler syndrome, coined by NASA scientist Donald Kessler, describes this phenomenon. How can we stop this orbital junk-generating chain reaction?
As we have seen in this video, space debris is a major problem. In order to avoid this, we have an idea with an efficient solution. A modular solar-powered satellite features a versatile robotic arm with flexible grips and nets for debris capture. It utilizes ion thrusters for the efficient propulsion and laser ablation system to manipulate small debris. The multi-sensor array, including LiDAR, radar, and optimal sensors, ensure real-time debris tracking. Units dock, collaborate, and provide backup for enhanced durability and mission success. Utilizing advanced sensors, a robotic arm, and a laser system, the satellite effectively manages space debris. Ion thrusters and solar power ensure suitable, scalable operation, modular swarm deployment. The unique selling point of our idea, which differentiate our idea from other pre-existing ideas. The AI-driven satellite is designed with a robotic arm to collect debris floating in space. It operates autonomously, thus detecting and collecting space debris on its own. Its scalable design incorporates modular components and swarm capabilities, allowing for extensive coverage and adaptability to various debris fields. The satellite incorporates ion thrusters that generate high thrust with very low fuel consumption. Now our team member Ayushman Soni will further explain our idea.
Hi, my name is Ayushman Soni. I am a team member from VAYUVARGA. Now, as we have seen, our USP is autonomous AI driven. So I'm here to tell you how it is going to be, how the coding and how the programming is going to be. So what are the technologies used for the MSDNU, which will be model-wise? First is robotic capture arm. The languages here that we are using will be C++ and Python because they are highly efficient, they're very good at data interpreting, and they are very user-friendly. For the hardware, we are using flexible robot arm with electro adhesion grips. For framework, we are using ROS for robotic control and simulation. For the debris removal, similarly, we are using languages such as C++ and Python. We are using hardware as laser system to alter debris trajectories. Sensors and detection. Frameworks that we'll be using will be TensorFlow and PyTorch, which are very efficient and very useful software libraries. Hardware such as LiDAR, radar, and optical sensors will be used. Frameworks similarly such as ROS for sensor integration and data fusion will be used. Now for the energy that we are going to give it to our energy panels or the systems will be obtained by expandable solar panels. So, communication and control will be using languages similarly such as Python and C++, and the hardware will be onboard computer for data processing and system control. For the framework, similarly, we are using ROS for communication between modules. Before diving into the feasibility and viability, I would like to introduce the collection unit. The collection unit is going to be a storage space for whatever the debris we have collected and thus stored. The collection unit will serve as a transponder, a transporter, and a storage unit for the space debris. Collection unit will be initially attached to our main satellite integrated system. As it is filled by the robotic arm fully, it will be further detached from the whole satellite system. It will be having its own ion propulsion systems that will guide it to its nearest space stations. The space stations, it will dock to the particular space stations, and thus it will carry and it will transfer all the space debris that it has been collected. The collected space debris are thus then transferred to a re-entry module or a reusable module that can be brought back to Earth or it can be used further. This is going to be a global collaboration project, and with the help of reusable rockets and many worlds and countries coming together, they can make this project very, very feasible. Now, coming on to feasibility and viability, now we are going to discuss challenges, risk, and strategies to overcome them. First is technological integration. Core technologies like robotic arms, laser application, and autonomous algorithms are individually advanced but require further testing and integration for high-speed debris operations. Since we know many technologies are to be integrated in our system, it is very highly complex and the complexity of our project will be increased. Resource management. High energy systems like lasers and robotics needs efficient power management. Lightweight materials, hence efficient solar modules are used. We'll be using composite materials or better materials for decreasing the weight and decreasing the mass of the whole satellite's integrated system and thus reducing our fuel consumption and reducing our overall thrust. Cost versus benefits. While initial costs are high, the long-term values lies in the reducing satellite collision risks, extending satellite lifespans, and lowering operational costs. Since it is going to be a global collaboration, the long-term benefits will be more. You can state it as a short-term loss, but in the long run, it will be beneficial to us. Scalability in market demand. Increasing demand for space sustainability, regularity supports, and scalable solutions like modular and swarm designs, integrated robotic arm to the satellite ensure broader coverage and mission viability. The scale of this project is going to be huge because space debris is a huge problem and the solution is going to be huge. Now I'll tell you what our collection unit will be like and how it will work. As you can see, the robotic arm over here where I'm pointing the cursor to, the robotic arm is filling the space debris into the collection unit. The collection unit is a open door or open storage that all the space debris are welcomed. As the space debris are put inside them, in the space debris are filled and the whole storage system is filled. Afterwards, it is going to be detached from this whole DD1 module and thus it is going to be going to our space stations. Here, global collaboration, as I said earlier, it's very important. Now I will show you a video where we will demonstrate how our collection unit will be integrated with our robotic arm and our satellite system and how it will be collecting the space debris around it. Now I will describe impact and benefits of our project. Firstly, social benefits. The primary social benefit will be increased public safety. Successful space debris removal reduces the risk of catastrophic collisions between space debris and satellites, manned missions, and possibly even Earth's surface. Second, educational inspiration. A successful project would inspire a new generation of engineers, scientists, and environmentalists. So, as you can see, the social benefits are going to be global. It is not restrained to a nation or to a continent or to a region. It is going to be a huge success. It is going to be a huge worldwide success that is going to be implemented. Now, impact on target audience. What will be our target audience? Primarily, it will be our space agencies such as NASA, ISRO, ESA, etc. More, more of our target audience will be commercial satellite operators, space tourism and space travel companies, researchers and academic private aerospace companies and general public. This will be our target impact audience, which will be impacting more because this is the field of expertise for them. Economic benefits, protecting and prolonging satellite infrastructure. Now, flick of a paint of a space debris can destroy a huge satellite, can destroy a satellite's communication from its own ground station, which can cost the satellite operator billions of dollars. This is the region where we come into the idea and we save that billions of dollars to so that we can invest somewhere in the good deeds. The space industry is highly reliant on functioning satellites for communication, navigation, and data. This project, if successful, would save billions of dollars by preventing collisions that could lead to loss or damage of satellites. Environmental benefits, lastly, the sustainable space programs. With a scalably modular system that can operate autonomously, the project would encourage more sustainable practices in space, ensuring the launching and operating satellites do not contribute to the worsening debris problem. Our environment will be cleaned, our space debris will be cleaned, our LEO, the low Earth orbit, which has been highly packed from the space debris, will be cleaned. This will impact on our space missions. It will be more cleaner. The probability of hitting our space debris will be much lesser, and it will be hence very good and very efficient to launch new missions. Concluding my PPT, I'll say this project is a small step towards a big goal to a clean aerospace, a big goal to remove all the space debris, a big goal to clean the Earth's orbit, and a big goal to improve our space travel and space tourism. I highly thank all my team members, all my mentors, thankfully Smarts India Hackathon for giving me this opportunity where I can present my idea for betterment of the society. Thank you.